Problem number 1, chapter 19. Two thermometers are calibrated, one in degrees Celsius and the other in degrees Fahrenheit. At what temperature in kelvins do their readings measure the same temperature? All right, let's think about this. We have a relationship between the Fahrenheit temperature and the Celsius temperature, and it looks something like this. My intuition tells me that that relationship looks right because at 0 degrees Celsius we should have 32 degrees Fahrenheit. So we put that in, at least that part works. And the Fahrenheit interval is greater than the Celsius interval by almost twice as much. So the 9/5 kind of fits. We want to find the temperature at which the Fahrenheit and Celsius temperatures were the same. So let's just say that we had the same T for both of these. So we'll say T equals 9/5 T plus 32. So we have the same temperature in Fahrenheit and Celsius, and solve this for T. So we'll have negative 32 equals 9/5 temperature minus temperature equals 4/5 T, or 4/5 T equals minus 32. T equals 5/4, which is negative 32, which is a negative 160 over 4. Gives me a negative 40 Celsius or Fahrenheit. Oh, no. Okay. But we want to find the Kelvin temperature that corresponds to this. This is minus 40 Celsius, and we know that the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. So that's equal to negative 40 plus 273.15 gives us 233.15 degrees Kelvin. So we select answer B. Problem number 2. A child has a temperature of 104 degrees Fahrenheit. What is the temperature in degrees Kelvin? Okay. We're going to start the same way as we did in the last problem. We'll have temperature Fahrenheit is equal to 9/5 temperature in Celsius plus 32. Let's solve this for the temperature in Celsius and then find the temperature in Kelvin. So, subtract the 32 from both sides. Multiply both sides by 5/9. So we have the temperature in Celsius will equal 5/9 times the temperature in Fahrenheit minus 32. We were told that the child's temperature was 104 degrees Fahrenheit. So let's put that in. This would be 5/9 times 72, and that comes out to be 40 degrees. We want the temperature in Kelvin, so we'll say the temperature in Kelvin is the temperature in Celsius plus 273.15. So that's 40. It's 273.15. Gives us 313.15 degrees Kelvin. At what temperature, problem number 3, at what temperature is the Celsius scale reading equal to twice the Fahrenheit scale reading? Okay, ready? Let's use the same relationship as we did in the previous two. Temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. But we were told that we want to find the temperature in which the Celsius temperature is twice the Fahrenheit temperature. So we're going to say that the Celsius temperature is twice the Fahrenheit temperature, and we're going to plug this into here and find out what the Fahrenheit temperature is. So we'll say that the temperature in Fahrenheit is equal to 9/5 times twice the temperature in Fahrenheit plus 32. So we'll have T sub F is 18/5 T sub F plus 32, or negative 32 is equal to 18/5 minus 5/5 temperature in Fahrenheit. Negative 32 is equal to 13/5 temperature in Fahrenheit, or the temperature in Fahrenheit is going to equal 5/13 times negative 32. And that is a negative 12.31 degrees. Fahrenheit. So we select answer A. Number 4, Death Valley in California receives many German tourists. When you convert a summer temperature reading of 130 degrees Fahrenheit to the Celsius scale they use at home, you find that the Celsius temperature is, first of all, I have to say, I don't know, if we go over to Germany, we go look at the castles, and we see all these great things built by human beings, and the Germans come over here and go to Death Valley to see nothing but a few cacti and stuff. Where were we? The temperature in Fahrenheit equals 9/5 temperature in Celsius plus 32. Let's convert this to the temperature in Celsius in terms of Fahrenheit. That would be equal to 5/9 times the temperature in Fahrenheit minus 32. Just subtracting 32, multiplying both sides by 5/9. And we're told that in Death Valley it's 130 degrees Fahrenheit. So we'll have 5/9 times 130 minus 32, or 5/9 times 98. And that gives us 54.4 degrees Celsius. Problem number 5. A student has written the equation below to convert a temperature in degrees Fahrenheit into Kelvin. What is wrong with this equation? And now it looks like T's Kelvin is equal to 9/5 temperature Fahrenheit plus 32. Well, let's actually come up with a relationship to convert temperature in Fahrenheit to temperature in Kelvin. We can start from this equation. Temperature in Fahrenheit is 9/5 temperature in Celsius plus 32. In the previous problem, we solved this for the temperature in Celsius in terms of the temperature in Fahrenheit. So we said that the temperature in Celsius is 5/9 the temperature in Fahrenheit minus 32. And if we convert the temperature in Celsius to the temperature in Kelvin, we would say the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. So this is equal to 5/9 the temperature in Fahrenheit minus 32 plus 273.15. So that should be the true conversion from Kelvin from Fahrenheit to Kelvin. In this problem, we were told that the student had written down the temperature in Kelvin was 9/5 the temperature in Fahrenheit plus 32. So what's wrong with this equation? Well, part A is correct. The factor in front of the TF should be 5/9. should have this factor here. Part B is correct. The numerical factor 5/9 should multiply the temperature in Fahrenheit minus 32, which it does here. And part C, an additional 273.15 kelvins must be added to the right side of the equation like we did here. So A, B, and C is correct. So D is more correct, that all the corrections above are required. Problem number 6. A bridge is made with segments of concrete 50 meters long. If the linear expansion coefficient is 12 times 10 to the minus 6 per degree Celsius, how much spacing in centimeters is needed to allow for expansion during an extreme temperature change of 150 degrees Fahrenheit? So we have a bridge. The segment is 50 meters long. And it's going to expand when the temperature gets warmer. The temperature goes from 0 degrees Fahrenheit, the temperature changes 150 degrees Fahrenheit. And we were given that the linear expansion coefficient was 12 times 10 to the minus 6. Per degree Celsius. And we want to find how much spacing we need to allow for expansion. Now this linear expansion coefficient was given per degree Celsius, so we need to change that change in temperature Fahrenheit to change in temperature Celsius. So let's do that. The change in temperature Celsius will be equal to 5/9 the change in temperature in Fahrenheit. So that's going to be 5/9 times 150, which will give me 83.33 degrees. 83.3 degrees Celsius. Now, we're going to have an expansion due to this change in temperature, and so we'll have some increase, which we'll call delta L, and we know that the change in length should equal the original length times a factor, which will be the linear expansion coefficient times the change in temperature. And this will be a unitless factor if this is per degree Celsius and this is degrees Celsius, so that would just be a number. That change in length will be the original length, 150 meters, times the linear coefficient, 12 times 10 minus 6, times 83.3 degrees. And that gives us 0.05 meters, or 5 centimeters. So we must allow for the beams to expand by about 5 centimeters. Number 7, a building made with a steel structure is 650 meters high on a winter day when the temperature is 0 degrees Fahrenheit. How much taller in centimeters is the building when it is 100 degrees Fahrenheit? The linear expansion coefficient of steel is 11 times 10 to the minus 6 per degree centigrade.
Good to go.
All right, well, in this problem we went from 0 degrees Fahrenheit to 100 degrees Fahrenheit. So our change in temperature is our final Fahrenheit temperature minus our initial Fahrenheit temperature, which would be 100 minus 0. It's 100 degrees Fahrenheit. But in order to use that linear expansion coefficient, we need to convert this to Celsius. I'll put this building over here too. So our Celsius temperature will equal, or change in Celsius temperature will equal 5/9 times our change in Fahrenheit temperature. 5 nights times 100. 500 divided by 9 gives us 55.6 degrees Celsius. And because of this change in temperature, the building is going to elongate. So we are going to start with some initial length of the building, which was given as 650 meters. And the building will elongate to a higher height. So we want to find out what that change in L is. Well, our change in length will equal our original length times a factor, which is the linear coefficient times the change in temperature, Celsius. So this will be 650 times the linear coefficient for steel, which is given as 11 times 10 to the minus 6, times our change in temperature, 55.6 degrees. And that gives us 0.397 meters. Which would be approximately 40 centimeters. So on this hot day, this skyscraper is going to increase in length by about, if I can do this about right, by about 40 centimeters, maybe about that far.
Okay.
Problem number 8. What is the change in area in centimeters squared of a 60 centimeter by 150 centimeter automobile windshield when the temperature changes from 0 degrees centigrade to 336 degrees centigrade? The coefficient of linear expansion of glass is 9 times 10 to the minus 6 per degree centigrade. Well, let's look at this windshield for a moment. We have two dimensions. We have 60 centimeters by 150 centimeters. Let's leave it in centimeters. So our original area is going to be the area of this rectangle, which would be 60 times 150, or 9,000 square centimeters. And our change in temperature, we went from 0 degrees Celsius to 36 degrees Celsius. So our change in temperature would be 36 minus 0, or 36 degrees. And we're given that the linear coefficient of expansion of glass was 9 times 10 to the minus 6 per degree Celsius. But we were interested in how much area the windshield is going to expand, so we need the area expansion. And the area expansion, which we'll call beta, is twice the linear expansion. So this would be 18 times 10 to the minus 6 per degree Celsius. So now we can find out how much area this is going to change. So we'll say our change in area is our original area times the area expansion coefficient times our change in temperature. And that will be 9,000 times 18 times 10 to the minus 6 times 36 degrees. If I multiply those three numbers together, I get 5.83 square centimeters. So the windshield's area will increase by 5.83 square centimeters. Problem number 9. Angela claims that she wears a cylindrical shaped hollow gold bracelet because it expands less than a solid one with a change in temperature. Clarissa claims that a cylindrical shaped solid gold bracelet expands less than a hollow one. Which one is correct, if either? You know, if we had a solid object and we were to heat it, it would expand, and hence you might have something, if we're looking at the area, let's just look at the area and expand it out. It might expand out to something like this, and so everything is expanding at the same rate. But if I had an object that had a hole and I heated it, it would also expand, and everything would expand, and the hole would expand outward as well. However, the object with the hole doesn't know that there's a hole there. It doesn't know that that hole is being occupied by nothing, or that it might be occupied by that same material. So it expands in the same way as it does if it had the material there. So the hole expands as well. And our net result is that everything expands at the same rate, whether it's the material or whether it's the nothing. And so in this case, neither of them are correct, Clarissa or Angela, because both the inner and outer circumferences increase in length.
Good.
Problem number 10. A gallon container is filled with gasoline. How many gallons are lost if the temperature increases by 25 degrees Fahrenheit? Note that the volume expansion of gasoline is 9.6 times 10 to the minus 4 per degree Celsius. Neglect the volume of the change of the container. Well, let's take a look at this one. It's problem number 10. We're going to start off with a gallon. So our original volume is 1 gallon. And our change in temperature was 25 degrees Fahrenheit. Let's immediately change that to Celsius, because our linear expansion coefficient is per degree Celsius. So we'll go, our change in temperature in Celsius is 5/9. Our change in temperature in Fahrenheit, so it'll be 5/9 times 25. And that gives us 13.9 degrees Celsius. So we'll say that the day starts off cool, and over the course of the day increases 25 degrees Fahrenheit, about 13.9 degrees Celsius. We'll have a change in volume of the gasoline as equal to the original volume times the volume expansion coefficient times the change in temperature. Now, what is the volume expansion coefficient? Well, that was given in this problem. I was thinking it was a linear was given, but it's the volume that was given. 9.6 times 10 to the minus 4 per degree Celsius. So that's what is going to go in there. So let's say our change in volume would be our original volume, and let's just put it in terms of gallons. So we have 1 gallon times 9.6 times 10 minus 4 times 13.9 degrees Celsius. So this will give us our change in volume in terms of gallons, which gives us 0.0133 gallons, or about 1.3% of what we started with. So we could save, if we fill up in the morning, we could actually get an extra 1.3%. Let's see, if gasoline costs $3, then that could be about 4 cents, save 4 cents. So if you had a 100-gallon tank at 4 cents a gallon, you could save $4 by filling up in the morning as opposed to filling up at noon or when it got hotter during the day. Now, if you have a car like mine, a rice burner that only can hold about a gallon or 2 at a time, then you're only saving about 4 or 8 cents. Problem number 11. An auditorium has a volume of 6 times 10 to the 3 cubic meters. How many molecules of air are needed to fill the auditorium at STP, which would be standard temperature and pressure? Well, let's establish what standard temperature and pressure is. Now, if we look at the temperature, a standard temperature that everyone can use is the freezing point of water, so that is in Kelvin, 273.15 degrees Kelvin. And the standard pressure is the pressure that everybody's normally associated with. It, either call it 1 atmosphere or 1,000 millibars, approximately. So, lost my spot here. We'll say that our standard pressure is 1 atmosphere, or 1.013 times 10 to the 5 newtons per meter squared. That is in the SI system units. In this case, we have an auditorium that has a volume of 6 times 10 to the 3 cubic meters. And we were asked to find the number of molecules in this room. Well, we're going to use the ideal gas law, and we have to use one form of the R constant. And since we're in the SI system, we're going to use meters cubed and newtons per meter squared and Kelvin. We're going to use the form of R, which is 8.31. There's another one where it's 0.0821 that we use when we're using liters and atmospheres, liters and atmospheres. We're going to be using newtons per meter squared and meters cubed. So we're in SI system. Start off with the ideal gas law, PV equals nRT. Let's find the number of moles, N, of this gas in the room. Number of moles is PV over RT. Put in our numbers. We always want to use Kelvin when we're using these formulas. Because Kelvin is the absolute scale, it starts from 0 and only goes positive from there. So that is our scale of choice. Oops, I put that in the wrong place. Volume up there, and if we calculate all these numbers out, we will get the number of moles of air in this auditorium, and that is 2.67 times 10 to the 5 moles. However, the question was how many molecules of air are in this auditorium. And we know that per mole there's Avogadro's number of particles. So we would say that the number of molecules is equal to the number of moles we have times Avogadro's number. And so that will equal 2.67 times 10 to the 5 times Avogadro's number, 6.022 times 10 to the 23 molecules per mole. And that will give us the total number of molecules, which is 1.61 times 10 to the 29 molecules of air in the auditorium. Problem number 12. 1 mole of an ideal gas is held at a constant pressure of 1 atmosphere. Find the change in volume in liters if the temperature changes by 50 degrees Celsius. We want to find the change in volume, and for this gas, it's an ideal gas, the ideal gas law will apply. So if we start from the ideal gas law, PV equals nRT, we're going to say that our final volume would equal nRT divided by our final pressure. But we're told that the pressure is constant in this case, so let's treat it like a constant. And we'll say that our final volume is all these constants times the final temperature. nR over P times the temperature. And for that matter, the initial volume will be nR over P times the initial temperature, because P is constant. So I can say then that my change in volume, which is my final volume minus my initial volume, will be equal to nR over P times my final temperature minus my initial temperature. Just taking this minus this. So, putting in my numbers, I have the number of moles. It's 1 mole of ideal gas. And the pressure was 1 atmosphere. So since the pressure was given as 1 atmosphere, I'm going to use the other version of the R constant. I'm going to use the 0.0821 version, because that's for atmospheres and liters. And we'll put in 1 atmosphere for the pressure. And our change in temperature was 50 degrees Celsius. So our expectation is that this answer in volume is going to be in liters. If I multiply all those out, I get 4.11. So as the temperature changes by 50 degrees Celsius, we have 4.11, expansion of 4.11 liters for this gas. Problem number 13. 1 mole of an ideal gas is held at a constant volume of 1 liter. Find the change in pressure if the temperature changes by 50 degrees Celsius.
Go.
This problem is rather similar to the last problem, only this time the pressure is constant. I'm sorry, the volume is constant at 1 liter. So we start from the ideal gas law. And let's solve this for pressure. But in this case, the number of moles are and the volume are constant. So we can say that our final pressure will equal this constant times our final temperature, and our initial pressure will equal this constant times our initial temperature. So our change in pressure, which is the final minus initial, will be this minus this. So I have a change in pressure, P final minus P initial is equal to nR over volume, T final minus T initial. Now we are given the volume in liters. So in order to keep the units consistent, we will use the R constant that has liters in it. So we'll have 1 mole times 0.0821 times 1 liter, 50 degree temperature change, and that will give us 4.11. Now the units of the pressure using this R constant would be atmospheres, so that would be 4.11 atmospheres. Change in pressure. Problem number 14. 1 mole of an ideal gas has a temperature of 25 degrees Celsius. If the volume is held constant and the pressure is doubled, the final temperature in degrees Celsius will be... Okay, so here's number 14. We're going to start with an ideal gas at a temperature of 25 degrees Celsius. So our initial temperature, 25 degrees Celsius, which would be 25 plus 273.15, which is 298.15 degrees Kelvin. We always want to switch over to that Kelvin if we're going to use the ideal gas law. Now we're told that the pressure is doubled from the initial value. Now the initial value, when PV equals nRT, so our initial pressure would be nRT over V. The volume is held constant, so we can say that our initial pressure is this constant times our initial temperature. And our final pressure, for that matter, would be that same constant times our final temperature. However, we're told that the pressure is doubled, so the final pressure is equal to twice the initial pressure. And if I use this expression, put it in here, and this one in here, I would have nR over V, final temperature, equals 2 times nR over V, initial temperature. Just substituting in for these two pressures. The nR over V will cancel on both sides because they're the same values. And we have that our final temperature is twice our initial temperature. So that is 2 times 298.15 Kelvin, which is 596.3 degrees Kelvin. It says find the change in temperature, find the final temperature in degrees Celsius. So a little tricky here, we have it in Kelvin here. We have to convert back to Celsius. So the temperature in Celsius will equal the temperature in Kelvin minus 273.15. So 596.3 minus 273.15 equals, I have 323.15 degrees Celsius. Problem number 15. A helium-filled balloon has a volume of 1 cubic meter. As it rises in the Earth's atmosphere, its volume expands. What will be its new volume in cubic meters if its original temperature and pressure are 20 degrees Celsius and 1 atmosphere respectively, and its final temperature and pressure are minus 40 degrees Celsius and 0.1 atmospheres respectively? Looking at problem number 15, let's write down what we know. So we have a bubble having a diameter, a helium-filled balloon has a volume of 1 cubic meter. And its volume expands. Its original temperature was 20 degrees Celsius. So that would be 293.15 Kelvin. Its original pressure was 1 atmosphere. So that would be 1.013 times 10 to the 5 pascals, newtons per meter squared. And its final temperature was minus 40 degrees Celsius. So that is 233.15 Kelvin. And the final pressure was 0.1 atmospheres. You know, actually, since we're going to be looking at ratios here, we can probably keep them in atmospheres because the units are going to cancel out. What we're going to do is we're going to say that P initial times V initial equals nR T initial, and P final times V final equals nR T final, which is true. And N and R are constants because we have the same amount of the gas constrained to be within the balloon. So the number of moles doesn't change. And of course, R is a constant itself. So I can say that from this first expression, that NR is equal to P initial, V initial over T initial. And from the second expression, I do the same thing. P final, V final over T final. In other words, it is true if we have a closed container in the same amount of gas, it is true that P initial, V initial over T initial equals P final, V final over T final for a closed container. We'll use this quite a lot, so let's save that formula for future reference. So in this case, we want to find the final volume. So let's solve this for the final volume. Let's multiply both sides by T final and divide both sides by pressure final. So V final will equal P initial over P final times temperature final over temperature initial times volume initial. And yes, the units will be canceling out in kelvins here and in atmospheres here. Now we did have to switch the temperatures to kelvins, because if you use centigrade, your ratios would not be correct. You have to go to the absolute scale. So we did have to do that, but we can get away with dividing atmospheres by atmospheres. On this one, we have then that our P initial was 1, our P final was 0.1 atmospheres, our T final was 233.15, our T initial was 293.15, and our initial volume was 1. So if I put all those values in there, I get 7.95 cubic meters. So this helium-filled balloon went from 1 cubic meter to 7.95 cubic meters, 8 times as much. I hope it is able to stretch a lot, otherwise it'll pop.
Good.
16. A bubble having a diameter of 1 centimeter is released from the bottom of a swimming pool where the depth is 5 meters. What will the diameter of the bubble be when it reaches the surface? The temperature of the water at the surface is 20 degrees Celsius, whereas it is 15 degrees Celsius at the bottom, and the density of water is 1,000 kilograms per cubic meter. We're given a bubble and we're given its diameter, 1 centimeter. But in order to use the ideal gas law, we need to know volume. So the volume of a sphere is 4/3 pi radius cubed. We need to put this in terms of the diameter. So we'd say that's 4/3 pi times diameter divided by 2 cubed would be 4/3 times 1/8 times diameter cubed times pi. So that will be, let's see, 4 divided by 24, or 1/6 pi diameter cubed. That's just the volume of a sphere. So we would say that our initial volume will be 1/6 pi, our initial diameter cubed, and our final volume will be 1/6 pi final diameter cubed. What else is given? We have the initial temperature is 15 degrees Celsius. We need to change that to the absolute temperature scale. So add 273.15 to that. So that is 288.15 Kelvin. Our final temperature was given as 20 degrees Celsius, and so we need to add 273.15 to that. So that is 293 0.15 Kelvin. So far, so good. Our final pressure is the pressure at the surface of the pool, which we assume to be the ambient pressure, 1 atmosphere. Our initial pressure is at the bottom of this swimming pool, which is 5 meters deep. Now I'm going to go with an approximation here, a slight approximation. And since it's pure water, we know that there is 1 atmosphere pressure for every 10 meters that you go down in the water, and that's a linear relationship. So that if you only go 5 meters, then you've added half an atmosphere. So our initial pressure is 1.5 atmospheres. So let's use the ideal gas law relationship. P initial, V initial over T initial equals P final, V final over T final. Solve this for the final volume. So the final volume would be P initial over P final times temperature final over temperature initial times the initial volume. If we put in our values, I also want to, let's go one step further here. Yeah, let's just finish this and then go one step further. So I have 1.5 over 1 is 288. No. Final temperature, 293.15 over 288.15 times initial volume. And that number comes out to be 1.526. So we have final volume equals 1.526 times initial volume. However, we were given the volume in terms of diameter. So, do I have enough room on the side here?
Yes.
Let's do this. We have 1/6 pi. Final diameter equals 1.526 times 1/6 pi initial diameter cubed. The 1/6 pi on both sides will cancel out. And so we have D final cubed equals 1.526 times D initial cubed. Let's take the cube root of both sides. So we have the final diameter is the cube root of 1.526 times the initial diameter. And if I take the cube root of 1.526, I get 1.15. So this is 1.15. Our initial diameter was 1 centimeter. So this bubble will increase to 1.15 centimeters, 15% in diameter, but about twice, a little bit more than twice the volume. Problem number 17. A scuba diver has his lungs filled to half capacity, about 3 liters, when 10 meters below the surface. If the diver holds his breath while quietly rising to the surface, what will the volume of the lungs be in liters at the surface? Assume the temperature is the same at all depths, and the density of water is 1 times 10 to the 3 kilograms per meter cubed. So, let's start off with our ideal gas relationship. We have P initial, V initial over T initial equals P final, V final over T final, because we have a contained gas within the diver's lungs, and so the number of moles is not going to change. R is not going to change either. we want to find the final volume. So the final volume will be our initial pressure divided by the final pressure times the final temperature over the initial temperature times the initial volume. Now in this case, let's write down, well, let's see. The initial volume was 3 liters, and we were 10 meters below the surface. Let's write these down. 10 meters below the surface is 1 atmosphere for every 10 meters that you go down below the water if it's pure water. So our initial pressure is 2 atmospheres, and our final pressure is 1 atmosphere because the diver makes it to the surface of the water and you're at the ambient atmosphere. Assume the temperature is the same at all depths. Okay. So, with this in mind here, our final volume will be our initial pressure 2 divided by our final pressure 1. The temperature is the same at all depths, so T over T is just cancels out, times 3 liters. That's 2 times 3, or 6 liters. So the lungs of this diver will increase to twice their capacity of 3 liters. Which one are we doing?
18.
18, okay, ready. Problem number 18. A square plate has an area of 29 square centimeters at 20 degrees Celsius. It will be used in a low temperature experiment at temperature of 10 degrees Kelvin when it must have an area of 28 square centimeters. What area must be removed from the plate at 20 degrees Celsius for it to have the correct area at 10 degrees Kelvin? The coefficient of linear expansion is 10 times 10 to the minus 6 per degree Celsius.
Okay, we're good.
All right, so we're going to start with a plate that has 29 square centimeters of area, but we're told that it must have an area of 28 square centimeters at this lower temperature. So let's try this. Let's assume it has 28 square centimeters at the low temperature. Let it expand to room temperature and just see what it would expand to, and then we'll cut our plate down to that size. Make sense? So let's try this. So let's assume that we start at the lower temperature. Our initial temperature is 10 degrees Kelvin, and our final temperature will be 20 degrees Celsius, which would be 293.15 degrees Kelvin. So our change in temperature will be 293.15 minus 10, 283.15 degrees Kelvin. We were given the linear expansion coefficient, alpha, as 10 times 10 to the minus 6 per degree Celsius, but we want the spatial coefficient, so we want beta, which is 2 times alpha. That's 20 times 10 to the minus 6. And I think now we're ready. We want to find the final the final area of this plate when we've gone from the low temperature to room temperature. So we're going to say that our final area will equal our initial area times 1 plus beta times our change in temperature. And this will be 28 square centimeters times 1 plus 20 times 10 to the minus 6. Change in temperature was 283.15. All that. And when I figure out, or multiply this out, add it to 1, multiply by 28, I get 28 0.159 square centimeters. So that's the size of the plate that we need at room temperature, so that when it is cooled down to 10 degrees, then it'll be 28 exactly. But we have a plate that's 29 already at room temperature, so we're going to have to cut that plate and take some away. And that was the question, is what area do we need to remove? So the area we need to remove is the area of the plate minus this. So that'd be 29 minus 28.159 gives us 0.841 square centimeters. Problem number 19, an open-ended problem. A gold ring has an inner diameter of 2.168 centimeters at a temperature of 15 degrees Celsius. Determine its diameter at 100 degrees Celsius. The linear coefficient of expansion for gold is 1.42 times 10 to the minus 5 per degree Celsius. Now in problem number 19, we're given the inner diameter of the gold ring, 2.168 centimeters, and we want to find the diameter after it expands. So even though it's a ring, and the ring itself is a three-dimensional object, and the circle of the ring is a two-dimensional area, we're looking at the diameter, which is a one-dimensional expansion. So we only have to worry about linear expansion in this case, not, I'm sorry, I moved out of your range. Linear expansion in this case, not volume expansion or area expansion. So, let's do this. Our final diameter will equal our initial diameter times 1 plus our linear coefficient times the change in temperature. And our initial diameter is 2.168 centimeters. The linear coefficient was given for gold as 1.42 times 10 to the minus 5. And our change in temperature was, we went from 15 degrees Celsius to 100 degrees Celsius. So our change in temperature will be 100 minus 15, or 85. So when I put all those numbers in there, I get 2.171 centimeters. So our new diameter is, what, 3/1000ths of a centimeter larger. Okay. Problem number 20. Determine the change in length of a 20-meter railroad track made of steel as the temperature is changed from minus 15 degrees Celsius to 35 degrees Celsius. The linear coefficient of steel, 1.1 times 10 to the minus 5 per degree Celsius.
Good.
So we want to find the change in length of a 20-meter long railroad track, and our initial length, let's see, this is problem number 20. 20 meters. We're given that the temperature has changed from minus 15 degrees Celsius to 35 degrees Celsius. So our final temperature is 35 degrees. Our initial temperature is minus 15 degrees Celsius. So our change in temperature is our final temperature minus our initial temperature, which will be 35 minus a negative 15 gives us 50 degrees Celsius. And we're given the linear coefficient of steel, which the alpha for steel is 1.1 times 10 to the minus 5 degrees Celsius to the minus 1. So this is just a one-dimensional expansion. So we'd say that our change in length will equal our original length times the linear coefficient times the change in temperature. And that will be 20 times 1.1 times 10 to the minus 5 times 50. And that gives us 0.011 meters, which we could write as 1.1 centimeters. So this track will expand 1.1 centimeters, enough that we should allow for it, otherwise it's going to buckle.